everybody. I'm Josh Berkus. For those who aren't familiar, I'm best actually known for working on the PostgreSQL project. But in recent life, I crossed over to the world of containers. I'm now working at Red Hat on Project Atomic. And of course, I think of these as two great tastes that taste great together. Hence this talk. Now, of course, I started this full auto database. By the way, any serious gamers here recognize the screenshot? This game I think only existed for about 6 months. No, was called Full Auto actually, and it was a sort of Car Warsy game. It sucked, but it made for great screenshots. And so one of the things I was thinking, is we're talking about sort of fully automated deployments of single master databases, which is what I'm going to be talking about here. But really, I'm not talking about this kind of full auto because with our single master databases, particularly some of your more mature ones like PostgreSQL, we're already pretty good at the complicated and scary department. What we really need for a full auto database is actually more like this, which is something that is friendly and cute and just does the right thing for you. We're not there yet, but we're working on it. So, also, before we get further here, I want to apologize in advance. This is more of a work in progress than a finished project. In my defense, a lot of the things that I'm waiting for to make this production worthy are coming in 1.2 and 1.3. So 1.2 isn't out yet, so there's going to be a lot of work in there. Plus, I got off onto a lot of yak shaving in the course of this project. Is anybody here not familiar with the term yak shaving? Few people, right? Yes, so forth. So this is an old sort of programmer hacker expression. Comes from the Perl community, which is basically just says, well, first you're fixing this thing. To fix that thing, you're fixing this other thing. And to fix that thing, you're fixing this other thing. And pretty soon you find yourself shaving a yak in Tibet, and you don't know how you got there. So when you take on one of these projects, a lot of happen. And actually, a lot of the yak shaving had to do with the Failover controller, which is a project called Patroni, which I will be going into more detail on later. But on the other hand, while it is not a finished project, it is working code, so I wanted to actually show you that. So I'm not entirely wasting your time. I've gone ahead and set up a little cluster here. We've got a couple. These are views from the cockpit UI, if you're unfamiliar with that. And so here is the cluster from a machine perspective. We've got 4 VMs here, as you can tell from the names. We're running on Amazon, which includes a KubeMaster and 3 kubelets on there, all running in Fedora Atomic Host, and each of these machines, let's actually take a look at them, is running a variety of services. This is also going to be the cluster for our demo at the booth later on, so we've got a lot more things running than just the database failover stuff. Here you can see in sort of Kubernetes view, we have a few services here. The service we're concerned with right now is the PostgreSQL service. Running on a few nodes here. PostgreSQL service, you can see, actually consists currently of 3 nodes that we have in our cluster. Because this is a database, there's no point in running more virtual nodes than we have physical nodes unless you have sort of unbalanced hardware resources. So we've got our 3 nodes, which actually got distributed out to the 3 virtual nodes. So we've got all that there. Now, one of the things that you can't actually tell through the Kubernetes view is that among those 3 nodes, we actually have 2 replicas and a master. So if you go ahead and look at it here, now, one of the things that we're exposing, and I'll explain how this goes later on, is an API that actually tells us what's going on in our little Postgres cluster. It's a RESTful API, so we've got a whole bunch of JSON. And this is actually the information in the various nodes. So let's see. First one's replica, second one's replica. Okay, third one's master. So we've got sort of our master node right there. Now I'm going to actually have to trace this back to where it's coming from, because this right here is the overlay address from Flannel. It's not the physical address of the machine. Overlay address is what we care about, because we care about having web services and other things connect to it. Since we only have... So we've got 2 replicas and a master. Now... Yep. Yep. Okay, there we go. Since we only have 3 nodes, I'm just going to take the quick way of looking and seeing and mapping this. One of the things on my to-do list is to actually write some code that maps it back to the physical address of the nodes. But for right now, I'm going to actually just introspect into the containers and see which one thinks it's the master. So this is going from the physical address here. This one does not think it's the master. This is the output of the Patroni Failover controller itself that tells you where it is in the replication stream. So that is not. So let's try. So again, we're looking at containers here, and we know okay, third time's the charm. I mean, obviously I know this one has to be the master by process of elimination, but I do want to show you the output here. Let's just look at running containers. There we go. So here we've got our leader, which is also another name for the master. So, like I said, the actual thing I've gotten off onto was a long time working on automated failover, which is the critical piece of this whole solution. So let's go ahead and demo that. So that was 189, which should be this one, number 3. Hold on, let's get out of here. So so let's look here. So we're now on the machine that is the current master here. And here is our container. So let's go ahead and kill the master. And remove it so that Kubernetes can't revive it. So a couple of things that are happening now, and so here we just lost the master. So there you can see the container output from the master. So let's see. Now it'd be nice if I could actually show you this happening in real time, but because of the distributed nature of this, it's a little hard to do. So let's actually look at. So we're going to look at one of the other kubelets here. So this one is still a replica. So let's see where we are here. And kubelet 2 here has promoted itself to master. Now, one of the other things that you'll see has happened since then is that because we define this as a service in Kubernetes, it has restarted Postgres on the 3rd node. Well, hopefully it's restarted it. Where is it? Oh, right there. And so that restart immediately joins the replication cluster only under the new master, which is on kubelet 2. So that's our first demo. Let's talk a little bit about what went into that and why. So, like I said, we're going to be talking about a single master databases. So single master databases have been a real problem for scalable services. Low availability is our primary problem, right? So you have unidirectional replication, where replication always has to go in the same direction from whoever's the current master to the other nodes. And generally, the high availability solutions that you see for single master databases tend to start with call the DBA, which is not very helpful for an always-on 24-hour service where you're allowed 5 minutes of downtime a year. This has actually been sort of a problem. And so one of the things you say is, hey, okay, well, let's just use a multi-master database. And I will tell you, as somebody who was a database consultant for 18 years, that regardless of the fact that there are more and better multi-master databases available now than there were in the past, most users are simply not prepared, are not mentally prepared for the differences between a multi-master and a single master database. I mean, first of all, depending on which database you're using, you're either going to get eventual consistency, which means you have to deal with inconsistency between nodes, or if you have a consistent multi-master database, then you're going to be dealing with high network latency on writes, particularly. You're going to have a lot of issue with a lot of these databases are very new, and they have a lot of issues around maturity and polish. Most of our available multi-master databases, especially in the world of open source right now, are non-relational databases. So relative to the older relational databases, they have a very limited feature set that then has to be re-implemented, particularly if you're using an application that was designed for a single master relational database and designed to take advantage of its features. So the multi-master databases can be a good solution for some problems, but they're not a good solution for all problems. We need to have a way to make the single master databases work from an availability standpoint. And the reason why this was particularly puzzling is that in the Postgres world, we have spent several years, decades of man years, in making Postgres replication absolutely bulletproof and reliable. As in, if you're not looking at it from a management availability perspective, you're looking at it from a does replication work, can I break it even if I try perspective, it's actually really, really good. So why don't we take advantage of that? And there's a lot of hesitancy and a lot of conservatism in the Postgres community. This is something I actually heard at a Postgres conference, said by somebody who is a committer to Postgres. And this is the common message that you get from DBAs and contributors to a lot of single master databases is, oh, auto failover, it's too difficult, it's impossible, it's whatever. And you don't want it. No, I want it. I absolutely want it. The alternatives are terrible. The alternatives are having your phone ring at 3 in the morning and still having everybody upset because it was down for an hour. It's just not sort of acceptable. I mean, the problem here is that I think a lot of people within the older databases have gotten confused between hard and impossible. But just because a problem is hard doesn't mean that it's impossible. Self-driving cars is a hard problem. I dare say a hell of a lot harder than auto failover databases. Right? But somebody is solving it. Getting pretty close to solving it. And frankly, from an engineer perspective, in a way, the hard problems are the only ones that are really worth solving. The other problems are not very interesting. So now, one of the reasons why this has been a problem is that every time somebody who's a career database person like me starts getting into doing auto failover and high availability, they try to solve it for everyone everywhere. They try to support the full feature set, and particularly the full scope of configuration that's available to the older database in order to support that. Now, that is an actual impossible task. You cannot be everything to everybody. But you can implement a solution that actually covers the most common use cases. Now, I actually looked at this. Part of it is that my career as a consultant prior to coming to Red Hat involved particularly doing a lot of consulting for Silicon Valley startups, a lot of social networking things, a lot of things like online coupons, a whole bunch of other stuff. And while we did do stuff like sort of billing systems and healthcare and that sort of thing that had a different set of requirements, for an awful lot of the stuff we were looking at, particularly for the stuff that we were looking at doing scale out on, it actually had sort of the same set of requirements, right? Which was you wanted to have a master, a pool of asynchronous replicas to basically act as your caching layer. You wanted to have a group of nodes that were cheap and replaceable. That by and large, your rule would be to replace them rather than fix them. And certainly containers have brought that philosophy into the forefront. Some kind of a watchdog service. You want to automatically promote one replica to the new master, have everybody else remaster against that new replica, and then update whatever routing or SDN or proxy that you have to the various replicas. This actually solves the problem for most people. There are trade-offs here. For example, I'm talking about asynchronous replication, which means that every time you have a failover, you're going to lose a couple seconds worth of, every time you have an unexpected failover, you're going to lose a couple of seconds worth of data. For a lot of applications, that's tolerable. There's some hand-wavy stuff now about reconfiguring this to do it with synchronous replication. Realistically, I think that's going to wait for PostgreSQL 9.6, which offers a better configuration for synchronous replication. But this is actually a solution that works for a lot of services and a lot of sort of problems. And that is completely implementable. So let's actually implement this. Now, so I'm going to offer a little history. Before there was Kubernetes or Docker or the sort of container philosophy or anything, I actually started this project called HandyRep as my first stab at sort of solving this problem. It's still out there and available on the internet. And the idea was to actually handle the sort of automated failover sort of majority use case. It had a sort of master controller architecture with a single HandyRep controller that controlled the whole sort of network based on Python Fabric and SSH. It's in production in a few locations. It was designed to work with any Postgres configuration and any sort of set of Postgres plugins that anybody happened to have. That was actually one of the requirements because I was doing it for a consulting company, and we had to support what our clients already had installed, not how we wanted them to set things up. Anyway, that's still out there. You can use that if that's your situation and if you're happy with that kind of a solution. There are some issues with the Fabric SSH architecture, but the problem was that we discovered with this is that by trying to support every configuration and plugin, we got something which was too general, and as a result, was really difficult to install and debug. Basically, the installation instructions, my consulting company was PostgreSQL Experts. The installation instructions for HandyRep were call PostgreSQL Experts, which was a good business for us, but not a general solution for the internet. On top of which, we'd kind of moved the single point of failure, right? The HandyRep server itself became a single point of failure, and there was a sort of thing for HandyRep failover, but it pretty much had to be manual because otherwise you risk split brain and a bunch of other things. So what I mainly learned off the HandyRep project was you can't solve the 100% problem, which is what I was trying to solve with that. Now, at the same time, another company called Zalando. Is anybody familiar with Zalando here? Yeah. They're a huge European fashion retailer. Happen to have a full sort of open source stack. Happens to be based on Postgres for database storage. So they have this huge sort of transaction rate. They need automated, decentralized HA, and they needed all of this, to sort of work. And they were actually trying to implement their own stuff as well, in parallel to me. And they were having a lot of issues with failover problems. Number one was false failover. That is when you fail over and you didn't need to, right? You only fail over because there's high traffic on one node, and as a result, it's not responding quickly, and you think it's failed, and then you fail over. There's a tool out there called pgpool, or pgpool 2 for Postgres, that sort of tries to implement automated failover for Postgres. It has that problem in spades, because its logic on when to fail over is very simple-minded. Misfires, that is attempts to fail over that don't complete, and so as a result, you end up having no master, and somebody has to intervene. And then, of course, because we're talking about distributed system here, race conditions are a big issue. But the biggest issue, our biggest sort of fear in the world of single master databases and failover is, of course, this one, split brain. Now, for a single master database, split brain is the worst possible outcome in almost every use case. That is, you would rather actually be down than to have split brain, because there is no automated recovery from split brain. Because what happens in a single master database with split brain is you now have two writable masters whose data can only be reconciled by hand by a human being. There's no sort of automated way to recover from that. There may be no manual way to recover from that, depending on what the level of disagreement is, and particularly what the nature of the data is. If you have an auction site, for example, and two people both bought the same item, there isn't really a manual recovery possible from that doesn't involve calling up a customer on the telephone. So one of the other tenets that became sort of a plank of any future system we design is that you're trying to avoid split brain at all costs, and that if you pursue this chain of logic to where your choice is, hey, are we going to risk split brain, or are we going to risk being down completely? You choose being down completely. So this is where our patron saint of HA, Patroni, comes in. It didn't actually come into the name Patroni, though. It came in actually with a blog post and some work-in-progress code posted by compose.io. So compose.io, another new platform as a service host, acquired by IBM. It's now part of IBM. I don't know, does anybody use Compose? So anyway, they had been supporting some multi-master databases like Mongo and that sort of thing. They had a lot of demand for Postgres. They wanted to support Postgres, but with the same kind of hands-off automated stuff that they were supporting like Mongo with. And they were like, and because there's a bunch of new guys, they weren't actually really burdened by previous assumptions about how you build an HA system. And so they actually posted this blog post and some, and again, some sort of sketchy working code. And that actually contained two things that turned out to be really, really valuable insights. Number one, Postgres is a poor store. It's actually a terrible store of its own replication state. That is, one of the problems with a single master database is you're going to have exactly the same data on the master and the replicas, barring any sort of network lag. Which means there is no way to actually store information for each node about what is my state, particularly if one of the nodes has become disconnected from the rest of the cluster. Now, this is a problem, if you look at my handy rep code, this is a problem that I go to elaborate lengths to work around, and I will tell you those workarounds do not work very well. But this was a problem that a lot of us in the Postgres world got into, is say, hey, we have a data store here, it's Postgres, the data store, let's store the state of the data store in the data store. What could go wrong? Well, lots of things, as it turns out. The other thing is that they actually decided that a smart agent system, where you have autonomous agents that each actually are programmed to do the right thing based on inputs and environmental factors is actually a better approach than a central controller. This was actually an approach that I had discarded earlier when working on HandyRep because I had seen a lot of dumb agents and therefore had discarded the smart agent approach. But we went back to it. So, and they introduced a project called Compose Governor that was based on containerization, based on using etcd for consensus. We'll go into that a little bit later, and a simple PostgreSQL controller. And so both I and the Zalando guys saw this at a Postgres event. We said that is what we need. We got together to collaborate on a project, and we forked Governor and created the Patroni project. So let's talk about how this is set up. Now, let's talk about failover again. So a lot of this single master stuff comes down to failover, right? Because you have one master, you have to control where it is failing over, how it is failing over, and where it's failing over to. So there's basically 3 parts here for failover. Number 1 is that you have to detect when the master is failed. And this is a complicated thing because failovers are not free, right? We can make them low cost, but we can never make them free. And therefore, you don't want to fail over casually when you don't need to. The second is actually failing over the master. And the third is making the applications fail over their connections. Now, where we are right now here is what we do with Patroni is that we use etcd keys with timeouts on a polling model in order to detect when the master has stopped sending new information. We have leader elections to determine who to fail over, where to fail over to, use Postgres built-in native failover once we actually have decided who's going to be the leader, and then the failing over the applications is the part that is currently the least finished mostly because I'm waiting for new Kubernetes stuff. But so let's talk a little bit about Patroni here. So what Patroni is that it's actually a controller program, a daemon, written in Python, that runs on each Postgres node and controls Postgres. So, and this is actually sort of a really important piece of the setup because the idea here is that if Patroni is not running, neither is Postgres. One of the other problems we got into in a lot of the older HA systems was to say, oh, what if the database is actually up but the controller is down? Well, the real trick is we need to make it not possible for the database to be up and the controller to be down. And this is actually where containerization in Kubernetes, because we'd previously been doing this all on VMs with the older solutions, containerization in Kubernetes suddenly really make it actually possible for us to make this work. It's a little Python daemon. It runs as PID1 in each container. It controls Postgres, startup, shutdown, config, provides an external RESTful API, and it enforces an opinionated configuration of Postgres. Because one of the other things it does is the way that you get Postgres on a machine is when you start up the node, the Patroni daemon actually creates your data directory and everything. So we can actually say, hey, yes, I know people want to do these sort of crazy things with having multiple Postgreses on one node, et cetera, and all this other stuff, but we're just not going to support that because it's an impossible failover situation. So the way that failover works here is, so we've got our Postgres node with Patroni, the Patroni agent here running in a Docker container. And we've set this up with a replication controller because, again, I'm doing this on Kubernetes 1.1. Will be replication set in the future. Set it up as a replication controller with 3 nodes in this case. And then when we deployed the 3 nodes, assuming we're deploying a fresh database, they actually become a blank slate. We don't actually currently have a master. So what happens is all those nodes connect to etcd. They have a leader election, and one of them becomes the master. And so that one becomes the master, it initializes, and then the other 2 recognize that they're replicas, and as soon as the master is available to serve data, they pull snapshots from the master and become replicas. Now, say that we actually kill the master like we just did in the demo. Well, then what's going to happen is both of these replicas have been pulling etcd to see if the master is still alive. And eventually they actually don't see a master key because it's timed out. So then they hold another leader election. One of them gets designated as the master. At that point, the other replica changes its replication direction to the master. Now, one of the things about this particular leader election, though, that's a little different from other systems. I mean, like, how many people work with leader elections with console, etcd, etc.? Yeah. So I'm not going to actually have time to get into this here because we're almost the Q&A section, but it's actually a two-stage leader election. We use the usual etcd mechanism, then it goes back out to the Patroni nodes. The Patroni nodes actually have a way of checking Postgres status because we don't, for example, want to elect a node as master that happens to be really far behind for a whole variety of reasons. Then we start replication, it's there. At this point, Kubernetes notices that we've lost a Postgres node. It redeploys the Postgres node, and that Postgres node finds out from etcd that there's a current master, and it pulls a snapshot from the new master and starts replicating. So what about split brain? Well, we're relying there entirely on etcd to help us prevent split brain. We think that's okay. It's what etcd is designed to do. Is anybody here not familiar with etcd? No, good. We got everybody here. It's what etcd is designed to do, and it does that pretty well, right? We wouldn't want to store data in etcd because from a write perspective, it's kind of slow. But from perspective of making sure that we have absolute consistency across the cluster, it's pretty good. We do actually have support for Zookeeper in Patroni if you prefer Zookeeper. It's been on my to-do list to implement console support. I haven't gotten around to it because I'm not personally using console. So it remains on the to-do list. So now Patroni talks all about failover. Now I've been working in, like, that was my whole episode of yak shaving. And actually, Patroni, where it is, except for we do have a list of issues and features. But in terms of the core set of managing failover and working in production, it's pretty much finished. It's already, like, Zalando took it, they deployed it in production, they've got it running a 150 database cluster. It's there. We will continue to work on it, but it's ready to go. Now we have to work on the whole rest of the stack, and this is actually what I've been working on my side of things. Now, we split off here. Zalando is very AWS-based. They implemented their own stack called Spilo, which is based entirely on the Amazon tools like CloudFormation and that sort of thing. I'm not so interested in that. I'm an all open source guy. So I'm implementing my stack based on Kubernetes with PostgreSQL, Patroni running on Atomic Host with Kubernetes, working on a dynamic proxy and an extension to Cockpit in order to have a UI actually particular to this. Actually, so I'm going down to Q&A problems, so I'm actually going to finish up with the slides, and then during Q&A I can actually poke around more if you want to. So, there are a few areas. Proxy is actually one of the major sort of core areas under development, and I've actually run into the problem here, which is that one of the things that Kubernetes is not set up to do with replication controllers or with deployment is differentiate between the idea that you would have a group of things in a group, but one of them has a special role without being a separate service. That is, the Postgres master versus the Postgres replicas. This is just really not sort of a mental construct, particularly when you have a complicated set of failover logic where something that happens internally on the pods themselves has to determine which one gets the new role. Right? So I have not been able to figure out a good way to do that. And then at this point, once I actually, read about a lot of the stuff that was coming in the way of the daemon sets and that sort of thing, it made me decide to actually wait for some of that before doing more major hacking on this. Currently what I have is some prototype, sort of stub stuff for using PG Bouncer. This is awkward. So PG Bouncer is a common proxy for Postgres. It also does event-based pooling, etc. So just having PG Bouncer, we have two PG Bouncers, one of which just redirects to the Kubernetes load balancer, and the other one of which runs some code, another Patroni-based daemon that pulls etcd to find out which machine, where the current master is. But this is really awkward. You've got two different addresses to connect to, depending on whether you're connecting to the master or the replica. We're running sort of extra pods, and we're running this completely outside of Kubernetes' understanding of where the services exist, which I don't like. There is some other features that we're working on for Patroni itself in terms of supporting other things, as well as supporting a bunch of other stuff. For example, there is a major multi-master Postgres project, and when that becomes production worthy, we want to have support for that as well. So, a few links, and we have a few minutes for questions, or I can just poke around on the screen some more and maybe do another failover.
So, does anyone have a question? Packed room.
Questions?
Must be someone.
So, on the timeouts of the keys in FTD, how long are they? Like, how long does the agent take to update those keys, or how does the agent keep track of them?
Okay. Yeah. So the question was the timing of the updates of the keys in etcd, and how does the agent keep track and that sort of thing. So, so there's two answers for that. One is the timing is actually a configuration setting. It currently defaults to 30 seconds, but you can change that. Setting it down below a couple of seconds wouldn't actually work materially, but and the way it works is you set the key with a time to live, right? And then if you don't set another update to the key, then when somebody requests that key again, they don't get it because etcd says this key's expired. I'm not going to allow you to read it. So it's effectively as if it were deleted. And again, the TTL is actually configurable, but defaults, I think, to 30 seconds.
Anyone else? Yeah. One in the middle.
Is it possible that you're writing into the master and you're getting your rights confirmed, and then your master dies, but it's not done replicating?
So the question was, you're doing your writes and the master dies and it wasn't done replicating. Since this is an asynchronous, since what we currently have is an asynchronous replication solution, that is absolutely possible. As a matter of fact, in an unexpected failure like a hardware failure, it is pretty much almost certainly what would happen. So you're going to lose a couple of transactions. And then when you bring up the new master will not have those transactions. Your alternative to that is to actually look at the sort of experimental synchronous replication support, which would prevent that from happening. But the drawback to synchronous replication, as it is for databases everywhere, is you've got this double network round trip, right? Because you have to write to the master and then it has to write to a replica before it acknowledges the write. But that's the only real way to prevent the lost writes. More questions? The question was, do you find you have to do node affinity and node selection? And the answer is yes. I've been doing that in a very ad hoc way, which is why I'm eagerly awaiting new releases. Because among other things, I'm actually using volumes on the host. And that would be a real problem if I was running more than one Postgres node on the same host, because it would share the same data directory, which doesn't really work. Yeah, so the question was volumes on the host and if they're ephemeral or cloud-based. So actually, my whole solution I'm working on is agnostic to how you want to set up your volumes. So that would be kind of up to you. I tend to take the approach for a lot of these solutions. So one of the questions that you have to decide when doing redundancy for Postgres and for other databases is, are you going to do your redundancy by preserving the data, that is persistent volumes or cloud storage, or are you going to do your redundancy by making lots of copies? And what that decision often comes down to is how big are your individual databases. If they're relatively small, then I recommend making lots of copies instead because it's a lot less headaches. If they're large, then let's look at putting that volume on some kind of cloud storage. But one of your problems the moment that that volume can persist beyond the depth of the individual pod is how do you make sure to prevent two different pods from accessing the same physical files at the same time? Because that could cause data corruption. So right now, I'm not solving that problem personally. If somebody has a good idea for how to solve that problem, well, actually, once again, waiting for some of the stuff like, say, PetSet, which I'll be having some input onto, in order to make that sort of thing work. Like, for example, naming them after the pods. Yeah?
So your example that you had on the slides where the third node comes back,
Yeah.
it could be the leader, now it's going to be a replicator. You assume, or you did an affinity, it was picking up the same node where it was in before.
It's not, because all I'm doing is I've got some stuff to make sure that I don't have more nodes than I have machines available. And under those circumstances, the default Kubernetes scheduler will put the new node on the machine that isn't already running one. It just automatically does that. Now, you notice one of the things I had to do, though, was that I had to actually remove the container, because since I wasn't actually terminating the virtual machine, if I don't remove the container, what Kubernetes will try to do is restart the existing container, which I wouldn't actually want it to do in that example, because then the existing container would try to come up as a master, discover it couldn't come up as a master, and not start.
Got time for one more question. At the back.
Question was, how do you do a major upgrade to Postgres? And the answer is, that's one of the things for which I am waiting for BDR and UDR, which are new Postgres features, to be a little bit more stable. Right now, those are on a fork of Postgres, and those will permit online major upgrades. Because right now, with Postgres built-in replication, you can't replicate it between major versions. So by Postgres 9.6, if we will be able to do online major version upgrades, it will still involve some thinking it out, because you'll need to run new versions of nodes, have them join replication, have them change the type of replication they're doing, because it's two different replication modes. We should talk about that later on, because it's complicated. It's coming. It's not quite available yet.
Great. Thank you very much.
Thank you.